Let's go ahead and try to solve for the mechanical advantage of a first-class lever. And so the definition of a first-class lever is a rigid bar with the effort force and the force resistance off on either side of the rigid bar and the fulcrum in the middle. Now, even though we say the fulcrum has to be in the middle, it doesn't have to be exactly in the center of the two. In fact, I'm going to draw my fulcrum a little bit closer to my force resistance than it is to my effort force. I'm going to draw it a little bit further to the left. And let's say our force resistance is equal to 50 pounds. And let's say we don't know what our effort force is equal to, but we do know what the distance from our fulcrum to our effort force is. Let's say that is 5 feet. And then let's set the distance from our force resistance to our fulcrum equal to 2 feet. And so I have two questions for you. The first one is, what is the mechanical advantage? And the second question is, what is our effort force in this first-class lever? And let's solve for our mechanical advantage first. Now, you might notice that we are given two distances and not two forces. And so I'm going to use our IMA-DIR equation. Our IMA is equal to our distance effort divided by our distance resistance. And so the question becomes, what is our distance effort and what is our distance resistance? Because if you look, this 5 feet and this 2 feet, that is not the distance traveled by our forces. That is the distance from our forces to the fulcrum, which is not exactly the same thing. And if you look at this effort force applied to this lever, what would happen is this effort force, the distance it would travel, is actually in a circle around this fulcrum or this pin on our lever here. And so what the distance effort would actually look like is just a big circle around our fulcrum. And so the distance traveled by our effort force would be along this perimeter of this circle, which is just a circumference. So let's go ahead and call that our circumference effort. And you may notice that this 5 feet would be the radius of that circle created by our effort force. So let's call that our radius effort. And then similarly, this force resistance will also create some circle around our fulcrum, only this time it'll be smaller since its radial distance is smaller. So let's call this our circumference of our resistance. And then let's label this 2 feet as our radius resistance. That is the radius of our circular distance resistance. And then we can rewrite our dE over our dr as our circumference of our effort divided by our circumference of our resistance. And you may recall the formula for circumference is just 2 pi r. And so we can rewrite this as 2 pi multiplied by the radius of our effort divided by 2 times pi times the radius of our resistance. And of course, we know those numbers, so we can rewrite this again to say 2 times pi times our radius effort is 5 feet. And we'll divide that by 2 times pi times our radius resistance, which is 2 feet. And we can simplify this. We can say 2 times 5 is 10, so we can write 10 pi on top. And then we know 2 times 2 is 4, so we can write 4 pi on bottom. And then to simplify those numbers, let's go ahead and type it in our calculator. 10 times pi is 3.14, so 10 times 3.14 is just 31.4. And so we can say this is equal to 31.4 on top. And then on bottom, we'll say, well, what is 4 times pi? So what is 4 times 3.14? And what do we get? We get 12.56. So on bottom, we will write 12.56. And what is 31.4 divided by 12.56? And let's try to get that decimal in there, 12.56. And what do we get? We get an IMA of 2.5. And you may be looking at this and be thinking to yourself, well, this formula for our IMA is a lot more complicated than it was in an inclined plane. We have to find these circumferences as well. We have to do all this extra math. Is there an easier way? And so let's examine this real quick. Let me show you a little trick. If we were to just look at this 10 over 4, if we were to say that pi canceled out, because pi divided by pi is just 1. If we were to say that canceled out, and we were just to say 10 divided by 4, what would we get? We'd get that exact same answer. And then we could go one step further. We could say pi cancels out over here, and then 2 over 2 also cancels out. And so what are we left with? We're left with 5 over 2. And so we try that in our calculator. 5 divided by 2 is also equal to 2.5. And so again, it is the same. And so what does that mean? Well, if we rewrite this equation right here, we could say 2 pi times the radius effort divided by 2 pi times the radius resistance. We can notice that 2 cancels out and pi cancels out, and so I can set this equal to our radius effort divided by our radius resistance, which would just be 5 feet over 2 feet. So on top we can write 5 feet, and then on bottom we can write 2 feet. And then we'll notice that feet cancels out, and so we're left with an IMA of 2.5. And so what does this mean? Well, what this means is our IMA equation, which is equal to dE over dr, is also equal to, in these circular kind of problems, our radius effort divided by our radius resistance. And so even though our radius effort is not equal to our distance effort, they're very different numbers. For example, our radius effort is 5 feet, whereas our distance effort is 31.4. As long as we set them equal to the proportion, it's the same. And so effectively, we can make 5 feet our distance effort, and we can make 2 feet equal to our distance resistance, and it would work the exact same way. But I'm a deer rolls off the tongue better than I'm a rear, I would argue. But only because it's easier to remember and a little bit more appropriate. And so we'll stick to this equation knowing we can use our radial distances for our dE and our dr. And so now what about our effort force? Well, to solve for our effort force, we need to assume an ideal effort force equation. So we need to assume our IMA is equal to our AMA, which means we can assume our drs, our free equation, our dE over dr, is equal to our FR over our FE. And if we assume this, we can go ahead and just plug in our numbers. We already know our dE and our dr is 31.4 and 12.56. But we've also already said that our dE over dr is equal to our radius effort over our radius resistance, meaning we can use this equation as a substitute for this equation, hopefully making everything a lot simpler and not having to worry about circumference in the future when it comes to levers. We can just write 5 feet over 2 feet as dE over dr, and we'll set that equal to our FR over our FE, and our FR is just 50 pounds, and we'll divide that by our FE, which we don't know. And so to solve for this, we'll just cross multiply and divide. And so we can say, well, 2 feet times 50 pounds on top, so we'll write 2 feet multiplied by 50 pounds, let's color code this, divided by 5 feet will be equal to our effort force. And so we could do this real quick without a calculator. 50 times 2 is 100, and 100 divided by 5 is just 20. And we can see that feet cancel out. And so what we're left with is our effort force is equal to 20 pounds. And so this video started a little confusing where we had to figure out all these circumferences, but hopefully by the end you saw that solving for the mechanical advantage of a lever or using our ideal effort force equation in a lever is no harder than it was in an inclined plane. And as you'll see in future videos, we can apply the same rules to second and third class levers.